We have seen construction rules for Bode plot. So far, only partially we have seen. Some more construction rules are there that we'll see today. So far, we have seen how to draw Bode plot for 1 by S, S in the numerator, and K. Now, let us see how to draw Bode plot for first order factor in the denominator. That is G of S equal to 1 by tau S plus 1. For that, how to draw the Bode plot that we will see now. To draw Bode plot, the first step is we have to convert this into sinusoidal transfer function. Replace S by j omega. 1 by j omega tau plus 1. That is the first step. Then we have to find the magnitude. What is the magnitude modulus of g of j omega that we have to find? That is equal to 1 by square root of imaginary part square plus real part square. This is magnitude plot. What is the magnitude? What is in decibel scale? That is 20 log modulus of g of j omega. That is equal to 20 log 1 by square root of omega square t square plus 1. That is equal to minus 20 log square root of omega square. For this, how to draw magnitude plot? We have to vary this omega from 0 to infinity. For that, we have to draw the magnitude plot. For that, we are considering two cases. The case one is omega tau is far greater than 1. Far greater than 1. And omega tau is far less than 1. Two categories. We are separating this into two cases. This equation is, for this we have to draw the Bode plot by varying omega from 0 to infinity. We are considering two cases. One is omega tau is far greater than 1. Another case is omega tau is far less than 1. If omega tau is far greater than 1, this is approximately equal to 1 is negligible. If omega tau is 1000 means 1 is negligible. Therefore, this can be written as minus 20 log square root of omega square t square. That is equal to minus 20 log omega tau. That's all. If omega tau is far greater than 1. Suppose omega tau is, this is for the case omega tau far greater than 1. That is case 1. In case 2, what we can say is omega tau is far less than 1. While compare with 0.001, let us assume 0.01. These are all negligible while compare with 1. That's why this can be written as minus 20 log omega tau is negligible because that is equal to 0.01 while compare with 1. Therefore, omega log minus 20 log 1, that is equal to minus 20 log minus 20 multiplied by 0. That's why 0 dB. So omega tau is far greater than 1 means the equation becomes minus 20 log omega t. If omega tau is far less than 1 means it is equal to 0 dB. 0 dB. Only two cases. Therefore, let us assume that when omega equal to 1 by tau, what will happen? When omega equal to 1 by tau, third case, when omega tau is less than equal to 1 by tau, we can replace omega tau by 1 by t. Therefore, it becomes, the equation becomes minus 20 log omega tau square root of omega equal to 1 by tau. 1 by tau square t square plus 1. T square getting tau square getting cancelled. Therefore, 1 plus 1, you will get 2. The third case is when omega equal to 1 by tau. When omega equal to 1 by tau, you will get the value 1. So, when omega tau is greater than 1 by tau, 1 is negligible. When omega is less than 1 by tau, when these two cases now we can define like this. When omega is greater than 1 by tau, it comes under this category. When omega is less than 1 by tau, it comes under this category. Because when omega equal to 1 by tau, it becomes 1. When omega equal to 1 by tau, it becomes 1. Therefore, when omega is greater than 1 by tau, it comes under this category. When omega is less than 1 by tau, it comes under this category. So, this omega equal to 1 by tau is the point that differentiates these two cases. When omega equal to 1 by tau, it is equal to 1. That point is called corner frequency. Omega equal to 1 by tau is called corner frequency. That point is called corner frequency. Now, let us assume that G of j omega equal to 1 by square root of omega square t square plus 1. Already, first case is what? When omega tau is far greater than 1 means omega square tau square is far greater than 1. That's why we can ignore 1. Therefore, G of j omega becomes 1 by square root of omega square t square, that is equal to 1 by omega tau. Therefore, 20 log modulus of G of j omega equal to 20 log 1 by omega tau, that is equal to minus 20 log omega tau. Here, we are considering only the cases omega tau is far greater than 1. Therefore, 1 is negligible. We will get when omega equal to 10 by tau, what you will get? When omega equal to 10 by tau, what you will get? Substitute omega equal to 10 by tau. I said 1 by tau is the point at which it is called the corner frequency. We are moving away from that point. How many times? 10 times, 10 by tau. If you substitute omega equal to 10 by tau, this value equal to minus 20 log 10 by tau multiplied by tau getting cancelled. 20 log 10 equal to 1. Log 10 equal to 1. Therefore, minus 20 dB. Suppose omega equal to 100 by tau, what will happen? Omega equal to 100 by tau, what you will get? Then you will get minus 20 log 100 by t multiplied by t. Therefore, power 2. Therefore, you will get minus 40 dB. Minus 40 dB. What is the distance difference between when omega 1 equal to 10 by t, omega 2 equal to 100 by t, 1 decade away? What is the decrease in magnitude? 20 dB. Therefore, it decreases at the rate of this is the 0.1. This is this is 1 by tau. This is 0.1 by tau. This is 10 by tau. This is 100 by tau. Suppose tau equal to 1, you will get conventional scale. Depends upon the tau value, you will get the scale like this. 1 by tau. What is the distance between these two? 1 decade. What is the distance? 10 times. Therefore, this is also 1 decade. Here at 1 by tau, after 1 by tau, After 1 by tau, at 10 by tau, its value is 20 dB. At 100 by tau, it is 40 dB. Therefore, it decreases at the rate of minus 20 dB per decade. It decreases at the rate of minus 20 dB per decade. Less than 1 by tau, it comes under this category. Less than 1 by tau, that is less than 1 by tau, it comes under this category. If less than 1 by tau, it comes under this category. Omega tau is negligible because it is fractional value. Less than 1 by tau means it is fractional value. Let us substitute omega is less than 1 by tau means let us put to 0.1 by t. If you put omega equal to 0.1 by t, t getting cancelled, 1 plus 0.1. 1 and 1 plus 1.1 both are almost equal. 1 and 1.1 are equal. Therefore, this can be ignored. This can be ignored when omega is less than 1 by tau. In that category, what you will get, that is left side of this point. Left side of this point, what you will get 0 because 20 log the magnitude is minus 20 log 1. Therefore, you will get 0 dB. Therefore, 0 dB. So this is the plot for 1 by g of s equal to 1 by tau s plus 1. For that, this is the frequency plot. Suppose I am having like this, g of s equal to 1 by 5s plus 1. Tau equal to what? 5. 1 by tau equal to what? 1 by tau. This implies 1 by tau equal to 1 by 5. That is equal to 0.2. Therefore, the corner frequency is 0.2. Corner frequency is 0.2 radians per second. Tau equal to 5. Corner frequency is what? 1 by tau. 1 by tau equal to 1 by 5 equal to 0.2. Therefore, corner frequency is 0.2. 1 by 2 should be labeled as 0.2. Am I correct or not? 10 by t means 10 multiplied by 0.2. That is equal to 2. 100 multiplied by 100 by t means 100 multiplied by 0.2. That is equal to 20. Am I correct or not? So the plot is like this. Up to corner frequency, it is 0. After that, it decreases at the rate of minus 20 dB per decade. Have you got? Still, you are having the confusion of 50. Corner frequency means 1 by tau. Corner frequency means omega equal to, we are assuming that omega equal to 1 by tau. At this point, 1 by tau means tau equal to 5. 1 by 5 means 0.2. Here, omega equal to 1 by 2, that is 1 by 5, that is equal to 0.2. Here, 10 by tau, that is 10 multiplied by 0.2, that is equal to 2. Here, 100 multiplied by 0.2, that is 20. Another example. G of s equal to 1 by 0.5s plus 1. Tau equal to what? 0.5. What is the corner frequency? Corner frequency equal to 1 by 0.5. That is equal to 2. Therefore, the plot for this is here. What is that? 0.1 by t. This is what? 0.1 by t. This is 1 by t. This is what? 10 by t. This is what? 100 by t. Now 1 by t equal to 2. Therefore, this becomes 1 by t becomes 2. This point is 2 radians. This is 20 radians. This is 200 radians. 200 radians per second. This is 0.2. Like that we can mark it. Because in the graph sheet, one division is what? 1 decade. So if you mark this as 0.2, this becomes 2. Therefore, up to 1 by tau, it is 0. After that, it becomes 0. After that, it becomes minus 20 dB per decade. After corner frequency, this is corner frequency. After corner frequency, it decreases like that. This is the frequency response for first order system. This is the frequency response for first order system. Suppose I'm having 0.5 s plus whole square. Then what you will get? G of s, G of j omega equal to 1 by square root of 0.5 j omega plus 1. 0.5 square j omega square plus, sorry, omega square plus 1 whole square. Whole square. That is equal to G of j omega equal to 1 by 0.5 square omega square plus 1. So in this case, modulus of. So if you square that, what you will get? You will get 1 by, let us assume 0.5 is tau. Generally, let us talk tau square omega square plus 1. Or what is the corner frequency? Omega equal to 1 by tau is the corner frequency. Before corner frequency, this is negligible. After corner frequency, this is negligible. Before corner frequency, tau square omega square is negligible. If you square 0.1, what you will get? 0.001. 0.01. Therefore, squaring means then also it is negligible. Fractional value. Therefore, before corner frequency, this is negligible. After corner frequency, this is negligible. Therefore, what you will get is 20 log modulus of G of j omega equal to 20 log 1 by, let us assume t instead of 0.2 for convenience, generalized case, t square omega square plus 1, because G of s equal to 1 by tau s plus 1 whole square. Therefore, you will get like this. This becomes minus 20 log t square omega square plus 1. When omega tau is far greater than 1, case 1, this is equal to minus 20 log t square omega square. That is equal to minus 40. If you bring that square here, minus 40 log omega tau. If second case, if omega tau is far less than 1, what you will get? Minus 20 log t square omega square is negligible. That's why 1, you will get 0 dB. So up to corner frequency 0. After that, it decreases at the rate of minus 40 dB per decade. It decreases at the rate of minus 40 dB per decade. Therefore, the plot is this is 0.1 by tau. This is 1 by tau. This is 10 by tau. This is 100 by tau. So up to 1 by tau, it is 0. After that, it decreases at the rate of minus 40 dB per decade. It decreases at the rate of minus 40 dB per decade. That's all. This is the plot for G of s equal to 1 by tau s plus 1 whole square. Suppose whole cube means it decreases at the rate of minus 60 dB per decade. Whole power n means it decreases at the rate of n multiplied by 20. Minus n multiplied by 20 dB per decade. Generalized case. Suppose now tau equal to, what we assumed, tau equal to 0.5. If you assume tau equal to 0.5, what is G of s? G of s equal to 1 upon 0.5 s plus 1 whole square. Therefore, this 1 by tau equal to 1 by 0.5 equal to what? 2. This becomes what? 0.2. This becomes what? 20. This becomes what? 200. That's all. That's all. Suppose tau equal to 10. 10s plus 1. 1 by tau equal to what? The corner frequency is 1 by tau equal to 1 by 10. That is equal to 0.1. Therefore, this point becomes 0.1. This is 0.01. This is, in that case, this becomes 0.1. This becomes 0.01. And this becomes 1. And this becomes 10. S plus 1 whole square. So it decreases at the rate of minus 40 dB per decade. So now we know how to draw for first order in the factor in the denominator. Suppose the first order factor is in the numerator. First order factor is g of s equal to tau s plus 1 in the numerator. What you will get? G of j omega equal to j omega plus j omega tau plus 1. Therefore, modulus of g of j omega equal to square root of omega square t square plus 1. Omega square t square plus 1. Up to corner frequency. What is corner frequency? Omega equal to 1 by tau. If you substitute omega equal to 1 by tau, it becomes 1. If corner frequency is omega 1 by tau, if omega tau is far greater than 1, it means it is on the right side of 1 by tau. Right side of 1 by tau. Omega tau is far greater than 1 means omega is far greater than 1 by tau. You understand this point now? Omega is far greater than 1 by tau. Omega tau far greater than 1 means omega is far greater than 1 by tau. So that is the category 1. In that case, 1 is negligible. You will get modulus of g of j omega equal to square root of omega square t square, that is equal to omega tau. So 20 log omega tau means 20 log omega tau means it is when omega equal to 1 by tau means 0 dB. When omega equal to 1 by tau. 20 log omega tau equal to omega equal to 10 by tau. You will get 20 dB. When omega equal to 10 by tau. When 20 log omega tau equal to 40 dB. When omega equal to 100 by tau. So it increases at the rate of 40 dB per decade. It increases at the rate of 40 dB per decade. But up to corner frequency, that is second case is omega tau is far less than 1. That is omega is far less than 1 by tau. Far less than 1 by tau. Therefore, if any point is the left hand side of corner frequency, that is negligible. That is 20 log 1, that is equal to 0 dB. Any point is less than 1 by tau, it is negligible. Any point greater than 1 by tau is considerable. Consider and you have to draw. Therefore, the plot is 0.1 by tau and 1 by tau. This is 10 by tau. This is 100 by tau. Up to corner frequency 0 dB. After that, it increases at the rate of 20 dB per decade. It increases. Therefore, when g of s equal to tau s plus 1, this is the frequency response. It increases at the rate of 20 dB per decade. If suppose g of s equal to tau s plus 1 whole square, it increases at the rate of 40 dB per decade. It increase after 1 by tau. After 1 by tau, omega equal to 1 by tau, it increases at the rate of 40 dB per decade. Suppose g of s equal to tau s plus 1 whole cube. After 1 by tau, it increases at the rate of 60 dB per decade. Like that, it will increase. So, without hesitating, we can draw the frequency response for a first order system. If we know 1 by tau, that's all. If you know the time constant, that is Corner frequency equal to 1 by time constant, Corner frequency equal to 1 by time constant. After that, it decreases at the rate of 20 dB per decade. Before that, it is 0 dB. That is the rough plot. That is, or in other words, it is called asymptotic plot. It is called asymptotic plot. For example, I am drawing a plot for a first order system. The asymptotic plot is up to 1 by tau, it is 0. After that, it decreases at the rate of 20 dB per decade. It decreases at the rate of 20 dB per decade. What is the actual plot? This is asymptotic plot. We are ignoring omega t if it is less than omega tau is far less than 1. If it is omega tau is far greater than 1, we are ignoring 1. If we consider both, what will happen? At corner frequency, what happens? That is equal to g of j omega 20 log modulus of g of j omega equal to 20 log 1 by square root of omega square t square plus 1. That is equal to minus 20 log square root of omega square t square plus 1. That is equal to minus 20 log. If you consider both at corner frequency, omega equal to 1 by tau. If you substitute omega equal to 1 by tau, what will happen at corner frequency? This is the corner frequency. At corner frequency, I am considering both terms. This is 1 by tau square multiplied by tau square plus 1. That is equal to minus 20 log square root of 2. You will get minus 3 dB. You will get minus 3 dB. If you calculate, you will get a minus 3 dB. Therefore, the frequency response, the actual plot is at this point, it decreases like this. Here, this is equal to minus 3 dB, 0 dB. Actually, up to corner frequency, we have drawn up 0 dB. But at corner frequency, there is an error of 3 dB. So, the asymptotic plot, that is the Bode plot. The difference between the Bode plot and the actual plot is, the difference between Bode plot and the exact plot is a difference of minus 3 dB only. A difference of, at that too at corner frequency only. Other points it is same, asymptotic plot. This plot is called asymptotic plot. Asymptotic plot. Because it is tangent at higher and lower values of omega to the actual plot. That's why Bode plot is asymptotic plot. It has an error of minus 3 dB at corner frequency. For a first order factor, it has an error of minus 3 dB at corner frequency. Suppose if it is a factor at numerator means here 0 dB up to corner frequency, actual plot is it will be 3 dB at corner frequency. Therefore, the error at corner frequency is 3 dB. Error at corner frequency is 3 dB. If you are not ignoring both omega tau as well as 1, you will get minus 3 dB instead of 0. Therefore, at corner frequency, you will get only minus 3 dB or plus 3 dB error. If it is denominator factor, minus 3 dB. If it is numerator factor, you will get 3 dB error. So we can consider the approximate plot because of small error. Suppose if you want the actual plot means, you can do the necessary correction at corner frequencies. That's all. Let us consider a case g of s equal to k multiplied by tau 1 s plus 1 upon tau 2 s plus 1 multiplied by tau 3 s plus 1. For this, how to draw the Bode plot, let us see. Now, let us consider k equal to 1 and tau 1 equal to 10s plus 1. Here, we will get 5s plus 1. Here we will get 20s plus 1. 20s plus 1. For k equal to 1 means 20 log k equal to 0. 20 log k equal to 0. That's why the plot for k is, when k equal to 1 means, the plot for k is at 0 dB, you will get a horizontal line. That's all. What is the plot for this 10s plus 1? What is the corner frequency for this? The corner frequency is 1 by 10. That is equal to 0.1. Let us say that this is 0.1, 0.01, 0.01. This is 0.1. This is 1. This is 10. This is 100. 1 by 5 is what? What is the corner frequency for this? 1 by 5. 1 by 5 equal to 0.2. What is the corner frequency for this? 1 by 20. 1 by 20 equal to how much? 0.05. 0.05. 0.05 is greater than 0.01. Am I correct or not? Okay. So everything is covered. So what is the plot for the numerator factor? What is the plot for the numerator factor? I am drawing the plot for numerator factor. Corner frequency is 0.1. Therefore, up to 0.1, it is 0. After that, it increases at the rate of 20 dB per decade. Am I correct or not? For this 5s plus 1, what is the corner frequency? 0.2. 0.2 is here. So 0.2 is here. Let us draw like this. To understand, let us put 0.1 here. This is 0.2. Corner frequency is 0.2 here. Corner frequency 2. This is corner frequency 1. This is corner frequency 3. Am I correct or not? I marked all these corner frequencies. Now I am going to draw the plot. The numerator, the corner frequency is 0.1. It is in the numerator. That's why up to 0.1, it is 0, approximate plot, asymptotic plot, Bode plot. Up to 0.1 is 0. After that, it increases at the rate of 20 dB per decade. It increases at the rate of 20 dB per decade. What is the plot for this? What is the plot for this? Corner frequency is 0.2. 0.2. Therefore, for that, it is up to 0.2, it is 0. After that, it decreases at the rate of minus 20 dB per decade. Up to 0.2, it is 0. After that, it decreases at the rate of 0.2, minus 20 dB per decade. The third case, 0.05 corner frequency. The third case is up to 0.05, 0. 0.050. After that, it decreases at the rate of minus 20 dB per decade. Am I correct or not? 3 plots I got. 4 plots actually. K equal to 1, that's why it is 0 dB always. 0 dB always. If you add all these 3 plots together, you will get the Bode plot for this. Bode plot for this you will get. You have to add all these together. This is for third factor. This is for second factor. This is for first factor. This is for first factor. This is for second factor. This is for second factor. This is for third factor. All the plots we have drawn separately, but we have to combine all these together. Here it goes up to infinity. It goes up to infinity. This goes up to infinity. This is also goes up to infinity. We have to add all these together. Up to 0.02, the second factor is 0. Up to 0.1, first factor is 0. Up to 0.05, third factor is 0. So after 0.05, some value is there. Am I correct or not? It is not 0. After 0.05, it is not 0. After 0.05, this factor is always there. I said it goes up to infinity. This factor is there. This factor is there. What is that? Third factor. The third factor, corner frequency is 0.05. So after 0.05, this factor is always there. After 0.05, up to 0.05, it is 0. Therefore, we can draw like this. We can draw like this. So this is 0.05, corner frequency 3. This is the corner frequency 3. Up to this, it is 0. Up to this, it is 0. After that, it decreases at the rate of minus 20 dB per decade because it is in the denominator. It is 1 by 20s plus 1. 1 by 20s plus 1. For that, the corner frequency is 1 by 20 equal to 0.05. Up to corner frequency, it is 0. After that, it decreases 20 dB per decade. Here, up to what point? Up to 0.1. Up to 0.1. Here, this is 0.1. Up to 0.1, it decreases at the rate of, up to 0.1, it decreases at the rate of 20 dB per decade. After 0.1, you see that what happens after 0.1, it increases at the rate of 20 dB per decade. One is increasing, another one is decreasing. If you add these two together, it becomes 0. One is increasing, the speed is positive direction. Another one is speed is in the negative direction. Both are equal. If you add it together, what you will get? 0. Therefore, no increase or no decrease. Am I correct or not? No increase or no decrease. Therefore, after that, it becomes horizontal. Why it becomes horizontal? For one factor, for this factor, it decreases. For this factor, after 0.1, it increases. Both are at same speed. One is increasing at the rate of 20 dB per decade. Another one is decreasing at the rate of 20 dB per decade. If you add these two speeds together, what is the speed? 0. There is no change in speed. There is no change in speed. That's why it remains in the same speed at 0 dB per decade. The slope becomes 0 dB per decade. Up to what? Up to 0.2 only. Up to 0.2 only. At 0.2, what happens? All the three graphs come together. What is the slope of this? Minus 20 dB per decade. What is the slope of this? Plus 20 dB per decade. If you add these two together, 0 dB. The third one comes into picture, minus 20 dB. Therefore, after this, again, it decreases at the rate of minus 20 dB per decade. Here, it is 0 dB per decade. Here, it is minus 20 dB per decade. If you add all these together, we got this plot. So this is the plot for the given transfer function. Suppose k equal to 10. Suppose k equal to 10. 10, what is the first? 10s plus 1 divided by 5s plus 1 multiplied by 20s plus 1. Now, earlier k equal to 1. That's why you got a horizontal line at 0 dB. Now, k equal to 10. For what is the k plot? 20 log 10. That is equal to 20 dB. Am I correct or not? For k plot, it is 20 dB per decade. 20 dB. That's all. 20 dB. This is the plot for k. Now, I change the sum. The second sum is k not equal to 1. It is 10. All other factors same. All other factors same. For all other factors, you got this graph. You combined all the three, you got this. Now you have to combine k also. K is equal to what? K equal to 20 dB. Here you got a line. This is 0 dB. This is 0 dB. 0 dB. This is 20 dB. Now we have to add this k with this. It means what? The entire graph will lift up by 20 dB. The entire graph will lift up by 20 dB. That's all. So here, the 0 dB, it starts at 0 dB. Instead, it will start here. After that, it comes down like this. Then it will be a horizontal line. Then it will. We shifted the entire graph by 20 dB. That's all. So, the K will shift the entire plot up or down. If K is greater than 1, it will shift the entire graph up. If K is less than 1, it will shift the entire graph by down. That's all. Now we got the Bode plot for 10s plus 1 divided by 5s plus 1 multiplied by 20s plus 1. We got. This is the plot for K equal to 1. That is 10s plus 1 divided by 5s plus 1 multiplied by 20s plus 1. That is the difference. If K is there, if K is greater than 1, the entire plot will shift up. Otherwise, it will shift down. That's all. This is to understand what is happening in the Bode plot. What is happening in the Bode plot? You can draw, if a transfer function is given, without doing any calculation, if you know the corner frequencies, you can draw the Bode plot. For example, in this sum, let us assume K equal to 1. What are the corner frequencies? What are the corner frequencies? Corner frequencies are 0.1, 0.2, 0.05. Am I correct or not? This is for 1 by 10. This is for 1 by 5. This is for 1 by 20. This is for denominator. This is also for this is for numerator. This is also for denominator. Am I correct? 5 is for denominator. Am I correct? Yes. This is for denominator. This is for denominator. This is for numerator. So, if I know the corner frequencies, first corner frequency is 0.05. So, up to 0.05, it is 0. After that, up to 0.1, this is in the numerator, up to 0.1, it decreases at the rate of minus 20 dB per decade. It decreases up to what point? Up to 0.1. After that, up to 0.2, it is horizontal line because both numerator, this is up to 0.1, it is in the numerator. At 0.1, it is in the numerator. Therefore, after that, it becomes horizontal. Again, up to 0.2, there are two terms in the denominator, one in the numerator. That's why 1 plus 20 and minus 20 getting cancelled. 1 minus 20 is there. Therefore, it decreases from 0.2. It decreases at the rate of minus 20 dB per decade. That's all. Now we will draw one K by 10s plus 1 multiplied by 0.1s plus 1. What are the corner frequencies? Corner frequency is 1 by 10. First corner frequency is 1 by 10, that is 0.1. Second corner frequency 1 by 0.1, that is equal to 10. First corner frequency is 0.1. Second corner frequency is 10. So I can draw the Bode plot. Let us draw the Bode plot for this. What is the Bode plot for this? What is the Bode? K equal to 1. Let us assume that K equal to 1. 1 minute. K equal to 1. For that, what is the up to 0.1? It is 0. After that, it decreases at the rate of minus 20 dB per decade. This is carries up to 10. Up to 10. Here, the corner frequency is 0.1. Up to 10, it is decreases at the rate of minus 20 dB per decade. After that, it decreases minus 40 dB per decade. Why? Why? There are another denominator factor. Here, it decreases at the rate of minus 20 dB. After 10 radians per second, another factor comes. That's why it decreases at the rate of minus 40 dB per decade. Therefore, this is the plot. Without doing any calculation, we can draw the Bode plot. Actually, this way we have to draw the Bode plot. For examination point of view, we need some data for the examiner. That's why we will see some systematic method to draw this Bode plot in the next class.